In this lecture, we are going to do a short primer on Q-learning in a financial engineering context. You can imagine this lecture as a shortcut to Q-learning if you couldn't bear to sit through 2 hours of pure reinforcement learning theory. Obviously, you should still do that, but this lecture might give you a different perspective. Okay, so unlike the previous trend-following code, in this lecture, our agent will actually learn and use its experience to improve future outcomes. So how can it do this? We start by introducing a concept called the Q table. The Q table is indexed by two things, the state and the action. You can imagine that if we put the states along the rows and the actions along the columns, we would get exactly what looks like a table, hence why we call this a Q table. You've already seen that actions can be represented by the integers 0, 1, and 2, so that makes sense. Action 0 corresponds to column 0, action 1 corresponds to column 1, and so forth. But what about the states? As far as we know, the states are not currently encoded as integers, so how can they index the rows of a table? This will be a topic for the next lecture, but for now, let's just assume that we will be using a Q table in exactly this form. Okay, so what does Q actually represent? The Q table represents the expected return for doing the action A while in state S. Note that you should not get reinforcement learning returns confused with financial returns. When I say return in this context, it means the sum of future rewards. So Q for state S and action A represents the sum of future rewards I will expect to get in the next time step, the time step after that, and so on. Using this definition, it becomes easy to decide what the optimal action is. Obviously, I want to maximize my future rewards. Therefore, I should pick the action that gives me the maximum Q. This might seem like circular reasoning, but let's assume that Q really does contain these expected returns. Then, it should be clear that if I find myself in some state S, I can use the Q table to determine what the best possible action is. I simply need to search through all the possible actions to find the maximum Q. That is, my policy should be to take the argmax over QSA for all possible actions A. So that takes care of how we should use the Q table, assuming it contains the right values. But how do we make sure the Q table contains the right values in the first place? For that, we need Q-learning. Since you've all been through the time series section of this course, you'll recognize that Q-learning is nothing but the exponentially weighted moving average. Firstly, we know that the return is recursive. The return at g at time t is equal to the reward at time t plus 1 plus the return g at time t plus 1. Similarly, we can estimate Q at the current state by taking one step, receiving the reward from the next state, and using the max over Q in the next state. We take the max, assuming that we will follow our policy and perform the optimal action on each step. So this is like taking the expected value of both sides. We'll call this a better estimate of Q, and we'll assign it the variable y. We'll call it y because it's a target. So how do we update Q? Q is nothing but the exponentially weighted moving average using y as the so-called new sample. So you can imagine this from the context of calculating the sample mean. To calculate the sample mean, we take the weighted sum of the new sample and the old estimate. Eventually, we know that this estimate will approach the true mean. Similarly, in Q-learning, we can think of y as our new sample and the Q on the right as our old estimate. We update Q by mixing these two into a new and hopefully improved estimate. Using basic algebra, we can rearrange this into a more typical form where QSA appears by itself and the error between y and QSA appears beside alpha. For my machine learning students, you may recognize this as gradient ascent or gradient descent. Note that this is the version we will see in the code, since it's closer to how Q-learning is usually presented. Okay, so that covers the two aspects of Q learning. How do we use Q to take actions? And how do we update Q so that our agent learns to perform optimal actions? If you recall, earlier we said that our agent object needs two functions, act and train. Knowing what we know so far, we can now write the pseudocode for our Q learning agent. Okay, so let's start with the act function. As you know, we don't just take the greedy action all the time. We have a small probability epsilon of performing a random action. This helps us balance the explore-exploit dilemma. We want to exploit what we think is the best action, but we also want to explore and collect more data so that our estimates improve. So in this function, we're going to generate a random number between 0 and 1. If this random number is less than epsilon, we simply sample a random action from the action space. Otherwise, we select the action, which is the argmax over Q, with a given state S for all possible actions A. Next, let's consider the train function. This function will take in an entire MDP transition as arguments. So we have state, action, reward, next state, and done flag. If done is equal to true, that means next state is a terminal state. We know that the value of terminal states is 0, since there can be no future rewards. Therefore, the target y is just the reward itself. Otherwise, we use the Q-learning formula to say that y is the reward plus the discount factor gamma times the max of Q given the next state over all possible actions. Then we update our Q table using the exponentially weighted moving average. So this lecture was a very brief introduction to Q learning, making use of the concepts we learned about earlier in the course. We now know how to use the Q table so that we can perform optimal actions. We also know how to update the Q table so that the values it contains are actually useful. These correspond to the two important functions of our agent class, which are act and train.